Hey everybody, and welcome back to another Chemi vid. So last video we covered general balances, and today we're going to cover mass balances, specifically steady state mass balances. But before we get into mass balances as a whole, we need to actually define what a mass balance is. We have this general formula, in minus out plus generation minus consumption equals accumulation. And like I said, that's the accounting for chemical engineering, but we need to apply it specifically to mass. So there is the law of conservation of mass. And as long as you're not dealing in the nuclear realm of things, we can assume that it's true, meaning that mass is neither created nor it's destroyed. It has to go somewhere. So the interesting thing becomes, in our general mass balance, the generation and consumption terms go away. We cannot produce mass, we cannot consume mass. So really our whole entire balance equation simplifies to in minus out equals accumulation. Now, let's talk about units of this. Because we're talking about movement of things, we're talking about things coming in and out of a control volume. Remember, things coming in and out of a control volume. Typically, we deal with mass flow rates. So we're talking about mass per time. So the in term is going to be a mass per time, and the way we denote that is an m dot. A dot signifies that it is a rate of something, so it's a per time, and the m stands for mass, so it is a mass per time. And we write a little subscript in, so we remember that it's all of the mass that's coming in, and we can even write a summation here because it is possible to have multiple streams entering into the same control volume, in which case we want to account for all of the mass that's coming in. Now we will subtract off the sum of all of the mass flow rates of the out. We could have, maybe 2 out streams out of this control volume. And now comes the accumulation term. This becomes a little more interesting because we can't write that as a flow rate, right? It's not going anywhere. It's inside the control volume, but it is changing with time. And so we write it as a derivative, dm dt. This is the mass balance, okay? It's the sum of all the inlet streams minus the sum of all the outlet streams is equal to this derivative term, dm dt. Notice there's no dot because the dt gives it that time unit that we want it to be in order for it to be consistent. This is a very important point though. Remember how I said we're not generating, we're not consuming mass? This is for non-reacting systems. Okay? That's very important. We're not changing one species into another. If I put 200 kilograms per second of NaOH into this control volume, the 200 grams of NaOH either has to be here or here, and the sum of these two has to equal 200. It's not going to go anywhere. It's very important that you remember this is for non-reacting systems. Now, I also said that it is steady state, and steady state means my flow in, my flow out, none of that is changing with time anymore. It's a single flow rate. So oftentimes with processes, let's say I look at a mass flow rate in of something over time, you will have this time that it takes to reach whatever value it is that you want it to reach. And from here to here, you can see the process is changing mass flow rate. And then from that point on, we're actually steady state. We stop changing. So that's what steady state is graphically. Mathematically, though, and especially in this mass balance or any other balance, it means that all time derivative terms equal 0. So that means that the dm/dt in the mass balance is equal to 0. It's very simple. Let's go ahead and do an example using this equation, and I think it'll be a lot easier to understand. So we're going to look here at a distillation column. We're going to distill benzene and toluene. We're trying to separate them. So you can see over here that we have a feed of 500 kilograms per hour of a 0.5 mass fraction of benzene. And we know that in the bottom portion, we have 200 kilograms per hour coming out, and we know that it is 96% toluene by mass fraction. But we know nothing about the top stream. We have no idea what's going on at the top of our distillation column, and we want to know. And the way that we find out is through a mass balance. So first, we need to draw our control volume. And the easiest way to do it is just to draw it through all of these entering streams around like that. So we've included the whole distillation column. We have one inlet and two, count them, 1, 2 outlets. Let's just go ahead and write our mass balances, right? So just so you remember, the mass balance is the sum of the mass in streams minus the sum of the mass out streams equals dm dt. Now, I forgot to tell you an important piece of information. This distillation column has come to steady state. It's no longer changing with time. So we can just go ahead and say that derivative is 0. So the sum of the mass in terms, well, that's just F. That's our mass flow rate, right? And the things that we have coming out, it's going to be minus the sum of the outstreams, which is T plus B. And that's all equal to 0. If I rearrange it, I know that F equals T plus B. That makes sense. Everything coming in is equal to everything going out in a steady state, non-reacting system. So it's as simple as plugging in the numbers, or we can symbolically solve for T here. We can see that T is equal to F minus B. Substituting that in, we know that 500 kilograms per hour is what F is, and we're going to subtract off the 200 kilograms per hour that we are getting out of the bottom. So we now know that T is 300 kilograms per hour using a mass balance. So now we need to figure out, okay, how much benzene is coming out the top? Or what's the concentration of benzene that's coming out the top? We don't know this mass fraction up here. Let's think about it. I could do a mass balance on benzene because all the benzene that comes in should go out the top or the bottom. It's not going anywhere else. And so why don't we go ahead and do a mass balance on benzene? So in our feed stream, you can see that if I take XB of the feed, the concentration of benzene in the feed, and multiply it by the feed, that's how much benzene is coming in. We're going to subtract it from how much benzene is coming out. So let's start on our top. We don't know XBT. We're going to multiply it times the top flow rate. Here we were given XT, but if you remember, the sum of all the components in a mixture or in a stream, their mass fractions is equal to 1. So I know that it's 0.96 of toluene, which must mean that XB in the bottom stream is equal to 0.04. So I actually know XBB, we just found it, and I can multiply it by B, and I know it's at steady state, so it just equals 0. Finally, all we really have to do is solve for XBT. So if we go ahead and solve for that, we will take XBF times F equals XBT T plus XBB B. So we're going to subtract this over and divide by T. So XBT is equal to XBF times big F minus XBB times big B divided by T. So if we go ahead and plug in those numbers, you will get the feed concentration is 0.5, and it's coming in at 500 kilograms per hour. We can subtract off the bottoms, which is 0.04, times the bottom's flow rate, which is 200 kilograms per hour. And we know that at the top we have a flow rate of 300 kilograms per hour because we solved for that prior. And so if you do the math, you get that XBT is equal to 0.81. So in this top stream, we have 300 kilograms of material moving through it. That's what we found here. And now we know that it is at a mass concentration of 81% benzene in that top stream. So I hope this example and this discussion of what a mass balance is really helps you understand what's going on. In a later video, we'll go over transient mass balances, so where we can get this whole response and describe the whole response of the system changing over time. But for now, we're going to stick to the non-reacting steady state systems.